Agriculture accounts for roughly 72%. Without a price tag attached to the resource, policymakers struggle to identify the actual economic value generated by each drop. In many developing regions, irrigation water is distributed through public systems at nominal, area-based rates. Farmers pay a flat fee based on the acreage of their land, rather than the actual volume of water they consume. Disconnecting the cost of water from its consumption discourages efficient resource allocation. It limits the financial recovery of public systems and restricts the capital needed to upgrade failing irrigation infrastructure. To solve this, resource economists use shadow pricing. When formal market prices do not exist, economists estimate the marginal economic contribution of unpriced goods using mathematical production functions based on observed farm behavior. To calculate the shadow price of water in the Pennaiyar Basin, economists tested 3 distinct methodologies: the residual value method, the Cobb-Douglas function, and the translog specification. These models allow us to move beyond simple volume to identify the specific factors, from labor coordination to physical delivery systems, that dictate water's true economic performance. To calculate the marginal value product of water, economists compile granular, farm-level crop budgets. These datasets track cultivated area, total output, and specific expenditures on human labor, animal labor, machinery, and material inputs. The residual value method calculates value through deduction. Economists subtract non-water input costs from total revenue, attributing the remainder to irrigation water. If non-water cost data is missing, the model artificially assigns that value to water, producing an inflated upper bound. The Cobb-Douglas production function uses a parametric approach, estimating specific output elasticities for each individual input. Its defining feature is constant elasticity, mathematically dictating that a 1% increase in irrigation water yields a fixed percentage increase in crop output. By forcing constant elasticity, the model assumes the relationship between water and machinery remains entirely fixed, regardless of how much of either is used. Both RVM and Cobb-Douglas struggle to represent how these production variables dynamically interact with one another in an actual field. They simplify the complex physical realities of agricultural systems. The translog specification provides a flexible economic reality. Introducing squared and interaction terms captures complex, nonlinear input relationships. The return generated by a liter of water changes drastically depending on the exact amount of labor, fertilizer, or machinery simultaneously present on the farm. Between 2019 and 2021, sugarcane cultivation registered negative marginal values for irrigation water. The translog equation's negative squared terms prove diminishing returns. Applying water beyond the physical capacity of complementary inputs, like labor or nutrients, actually destroys economic output. We can contrast this physical limitation with the temporal data recorded during the severe drought year of 2020 through 2021. During this period, rainfall dropped to a basin low of 821 millimeters. The translog model shows that as rainfall plummeted, the marginal economic value of irrigation water spiked significantly. Irrigation water achieves its highest economic productivity only when natural rainfall fails to meet crop needs and when the farm has balanced the complementary inputs required to receive that water. Measuring variation across time is only half the equation. The exact same volume of water yields vastly different economic returns depending on its physical location. The Kolmogorov-Smirnov test distributions across the Pennaiyar River Basin reveal massive spatial clusters where water application generates wildly different returns. The Villapuram district consistently registers the highest marginal water value, reaching over 4 rupees per acre for paddy. This high economic return is a direct function of physical infrastructure. Villapuram relies on 845 kilometers of highly integrated canal networks. This integrated infrastructure provides farmers with precise field-level control. Because the water delivery is reliable, farmers can synchronize irrigation with their machinery and labor schedules. Villapuram's efficiency contrasts with the Cuddalore district, where the marginal application of irrigation water proves significantly less valuable. Cuddalore naturally receives heavy annual rainfall. This natural abundance means the marginal addition of pumped irrigation contributes very little to the final crop output, rendering the engineered water economically redundant. The lowest economic returns appear in the Dharmapuri and Krishnagiri districts. Both districts possess large physical water storage reservoirs, yet they yield very low economic values for their water. The constraint here is an engineering failure. Fragmented distribution networks mean that the water stored in the reservoirs cannot be predictably delivered to individual fields. Because the delivery is fragmented, farmers cannot coordinate their water usage with their fertilizers, labor, and machinery. The translog model proved this coordination is mandatory for high yields. Reservoir capacity and water volume do not generate economic value on their own. Infrastructure quality and systemic integration are the variables that dictate the true value of water. The spatial variance proven by the economic models requires policymakers to accept a specific reality. Assigning a uniform, basin-wide economic value to irrigation water is a mathematical fallacy. Current national water policy relies on an area-based pricing model. It charges a flat rate per acre across the board, completely detached from marginal productivity or actual water volume used. This uniform pricing structure fails because it cannot account for the extreme spatial and infrastructural variance between a highly integrated district and a severely fragmented one. To achieve efficient resource allocation, uniform pricing must be abandoned. Authorities must implement a policy matrix that adapts to the physical realities on the ground. Policymakers must tailor their mechanisms to the physical integration of the infrastructure found in each specific district. This matrix plots infrastructure integration against marginal water value, providing a blueprint for modern water management. High-performing districts like Villapuram map to the top right quadrant, representing high value generated by highly integrated canal systems. The policy solution for this quadrant is volumetric pricing. By installing flow measurement devices at canal outlets, authorities can implement market-based pricing to drive efficient allocation. Fragmented districts like Dharmapuri map to the bottom left quadrant, representing low-value and fractured delivery systems. Attempting volumetric pricing here would be ineffective. Policy in this quadrant must prioritize capital investment in canal rehabilitation and tank integration first. Raising the marginal productivity of water through physical infrastructure upgrades is a mandatory prerequisite before any pricing reforms can function. True resource economics requires pricing the performance of the entire agricultural system architecture. Only by understanding how inputs interact can we move beyond the illusion of simply pricing the water.